Welcome back to Things I Know Nothing About, the show where we dive deep into topics we're just learning about, and hopefully you learn something new with us. Today, Maya, we're talking about something truly monumental that just happened, or rather is happening right now. Artemis 2.
Oh, Alex, this is absolutely incredible. We're talking about humanity's return to deep space, a crewed mission heading towards the moon for the first time in over 50 years. The launch itself on April 1st, 2026, from Kennedy Space Center's Launch Complex 39B was apparently flawless, a sight to behold, and it truly marks a new era in space exploration.
It certainly does. And while the initial launch and the crucial translunar injection burn, which essentially slingshots them towards the moon, were successful, it's a deep space mission with humans on board. That phrase alone sends shivers down my spine, because it inherently carries so many risks and a lot can still go wrong.
Absolutely. It's easy to get caught up in the excitement of a successful launch. Seeing those four astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, on their way. But we need to remember this is a test flight, designed to push the limits and gather critical data. The Orion spacecraft is their home and their lifeline for this entire 10-day journey, and every single system on board is absolutely vital.
So let's start with the heart of the matter. The Orion spacecraft systems, you mentioned it's their lifeline. What are the most critical systems that could malfunction, and what are the potential consequences of even a seemingly minor issue?
Well, you can think of Orion as a miniature self-contained world for these astronauts. The life support system is paramount, ensuring they have breathable air, fresh water, and a way to remove carbon dioxide and manage waste. A failure here, say an oxygen tank leak, a water purification system breakdown, or even just an issue with the CO2 scrubbers could quickly become catastrophic, creating an uninhabitable environment within hours or even minutes.
That's incredibly sobering to think about. I remember hearing early reports, even in the first few days of the mission, about a slight toilet issue and an unexplained smell. While these might sound trivial to us on Earth, in the confined, unforgiving environment of space, even something minor like that could be a canary in the coal mine, couldn't it?
Precisely, Alex. Those minor anomalies are exactly what mission control and the crew are trained to watch for. A slight toilet issue isn't just about inconvenience, it could indicate a plumbing problem, a pressure seal leak, or even a precursor to a wider environmental control system issue. The unexplained smell is even more concerning, as it could point to an electrical short, an overheating component, or the release of a noxious chemical. In space, there's no popping down to the hardware store for a spare part or airing out the cabin by opening a window. Every tiny problem has the potential to escalate if not identified and mitigated quickly, potentially jeopardizing crew safety or the overall mission success.
So, beyond life support, what about the systems that actually move and control the spacecraft? I'm thinking about propulsion, power, and navigation.
Each of those is a complex web of interconnected components. Alex propulsion, for instance, involves the main engine and a series of smaller reaction control system thrusters. The main engine is crucial for major burns like the translunar injection, but the thrusters are equally vital for fine-tuning the trajectory, orienting the spacecraft, and performing delicate maneuvers. A failure in any of these, a stuck valve, a faulty igniter, or even just a fuel line obstruction could leave Orion unable to adjust its course, potentially sending it off target or, in a worst-case scenario, unable to return home.
And power, I imagine, is just as critical. Without power, nothing works.
Absolutely, power comes from solar arrays, which convert sunlight into electricity, and batteries, which store that power for times when the solar arrays aren't facing the sun or for peak demand. If a solar array fails to deploy, or if there's a problem with the power distribution units or the batteries themselves, the crew could face a rapid depletion of resources. This could lead to a cascading failure of other systems, forcing them to power down non-essential equipment or even critical systems to conserve energy, potentially leaving them blind or unable to communicate.
That brings us to navigation and communication. Being lost in space without a way to talk to Earth sounds like the plot of a terrifying movie.
It's a very real fear for mission planners. Navigation relies on incredibly precise instruments like inertial measurement units, star trackers, and closer to Earth GPS. But once you're in deep space, beyond the reach of GPS, it becomes a game of celestial mechanics, calculating positions based on stars and Earth-based tracking. A malfunction in a star tracker, for example, could leave the spacecraft with an imprecise understanding of its orientation and position. Communication, on the other hand, depends on a delicate dance between antennas on Orion and the deep space network here on Earth. An antenna failure, a transmitter issue, or even just being in the wrong orientation could lead to an outage, leaving the crew isolated and unable to receive critical commands or report anomalies.
So, let's pivot a bit. One of the biggest differences between Earth orbit and deep space is the environment itself, specifically radiation. How big of a threat is radiation exposure to the Artemis 2 crew?
It's a huge concern, Alex, and perhaps one of the most insidious threats on Earth. We're largely protected by our planet's magnetic field and atmosphere. But as Artemis 2 travels beyond Earth's protective bubble, especially through areas like the Van Allen belts and out into interplanetary space, the crew is exposed to much higher levels of space radiation. This primarily comes in two forms: solar particle events, like solar flares and coronal mass ejections, and galactic cosmic rays, which are high-energy particles from outside our solar system.
I understand solar flares can be quite sudden and intense. What happens if one hits while they're en route?
A sudden, powerful solar flare, known as a solar particle event or SPE, can unleash a torrent of high-energy protons and other particles. While Orion has radiation shielding and mission planners constantly monitor solar activity, an unexpected or particularly intense event could still expose the astronauts to dangerous doses. Acute effects can include radiation sickness, nausea, vomiting, fatigue, and damage to bone marrow. Long-term risks are even more concerning, including an increased lifetime risk of cancer, damage to the central nervous system, and degenerative diseases. NASA has designated storm shelters within Orion with enhanced shielding, but these offer only partial protection, and the crew would have to hunker down potentially for hours.
That sounds incredibly dangerous. And what about trajectory deviations and navigation errors? Even the slightest miscalculation over such vast distances could have enormous consequences, couldn't it?
Absolutely. Think about the precision required. They're aiming for a lunar flyby, essentially a slingshot around the moon, and then a precise return to Earth. While the initial trajectory burns were successful, space is dynamic. Small gravitational perturbations from the Earth, the Moon, and even the Sun can subtly alter their path over time. If the spacecraft is even a fraction of a degree off course after the translunar injection, that deviation will compound over hundreds of thousands of miles, potentially leading to a significantly off nominal trajectory.
So, if they do deviate, they need to make corrective maneuvers. What if those corrections go wrong, or if the propulsion system needed for those corrections fails?
That's the nightmare scenario, Alex. The Orion spacecraft relies heavily on its main engine and the smaller reaction control system thrusters for these trajectory corrections. If an engine misfires, provides insufficient thrust, or worse, if there's a complete propulsion system failure, the crew could find themselves unable to adjust their path. This could mean missing their intended lunar flyby altitude, entering a dangerous trajectory that doesn't bring them back to Earth safely, or even stranding them in deep space. There are backup systems, of course, but deep space missions operate on such fine margins that even backups need to be perfectly executed.
This leads us directly into a broader discussion of engine burns and propulsion system failures. Beyond trajectory corrections, what other critical burns does Orion need to perform, and what are the failure points?
Well, for Artemis 2, the primary big burns were the translunar injection to get them to the moon. But throughout the mission, there will be multiple smaller burns called mid-course corrections to fine-tune their path. And critically, there will be a burn to orient the spacecraft for re-entry into Earth's atmosphere. Each of these burns is a moment of heightened risk. Imagine a fuel line blockage, a valve that sticks open or closed, or an issue with the propellant tanks themselves. These are incredibly complex systems with high pressures and volatile propellants. A propulsion failure could mean they can't achieve the proper velocity or direction for their return, or can't orient the capsule correctly for the scorching heat of re-entry.
The thought of them being unable to properly orient themselves for re-entry is terrifying. That brings us to what many consider the most hazardous phase of any space mission: re-entry and splashdown. What are the specific risks involved there?
You're absolutely right, Alex. Re-entry is a controlled catastrophe. The Orion capsule will hit Earth's atmosphere at speeds exceeding 25,000 miles per hour. The friction generates extreme temperatures, upwards of 5,000 degrees Fahrenheit, which is hot enough to melt most metals. The heat shield, which is a thick ablative layer, is designed to slowly burn away, carrying that heat with it, protecting the capsule and its occupants. If there's any damage to that heat shield from micrometeoroid impacts, launch vibrations, or even manufacturing defects, it could compromise its integrity, leading to catastrophic overheating inside the capsule.
So the heat shield is critical, but then once they've slowed down, they still need to get safely to the surface. What about the parachute system?
The parachute deployment sequence is incredibly complex and perfectly timed. Orion will deploy a series of drogue parachutes to stabilize and slow it down, followed by 3 massive main parachutes. Each one must deploy correctly, inflate properly, and function as designed. If even one of the main parachutes fails to deploy or snags, the capsule's descent rate could be too high, leading to a much harder splashdown than anticipated, potentially injuring the crew or damaging the capsule's structure. We've seen issues with parachute deployment on previous missions, so redundancy and robust testing are absolutely essential here.
And then the actual splashdown itself. It's not just about hitting the water, it's about doing so safely and then being recovered.
Exactly. The capsule has to hit the ocean at a precise angle and speed. A rough splashdown could cause internal injuries to the crew or even breach the capsule, compromising its watertight integrity. And then there's the recovery operation. The capsule could land hundreds of miles from the recovery ship in rough seas or even in an unexpected location if trajectory errors persist. The recovery teams need to locate the capsule quickly, secure it, and safely extract the crew, all while dealing with potentially challenging environmental conditions. It's a logistical ballet that has to be executed flawlessly under pressure.
We've talked a lot about hardware failures, but what about the human element? Even with extensive training, human error is always a factor in complex missions, whether from the crew or ground control.
Human error is indeed a perennial risk, Alex. On the crew's side, despite thousands of hours of training, simulations, and procedures, fatigue, stress, or even a momentary lapse in concentration could lead to an incorrect maneuver, an improper system operation, or a misinterpretation of data. Think about the sheer volume of checklists and procedures they have to follow, especially when dealing with an anomaly. One skipped step, one misread gauge, and the consequences could be severe.
And on the ground, with mission control, they're dealing with vast amounts of data, making critical decisions in real time. That must be incredibly challenging.
It is. Ground control is a highly skilled team, but they're still human. Errors could stem from software glitches, incorrect commands being uploaded to the spacecraft, or a misinterpretation of telemetry data. For example, if a sensor gives a faulty reading and the ground team acts on that incorrect information, they could issue commands that put the spacecraft or crew at risk. The Apollo 13 incident, while not exactly human error in the sense of a mistake, highlighted how critical the real-time problem-solving and decision-making by both the crew and ground control are under extreme pressure, and how easily things can go wrong even with the brightest minds involved.
Finally, let's talk about something that feels almost random, but is a persistent threat in space: debris or micrometeoroid impacts. Is this a significant concern for Artemis 2, especially outside low Earth orbit?
It absolutely is. Alex, though the nature of the threat changes slightly outside of low Earth orbit. In LEO, the primary concern is human-made space debris, defunct satellites, spent rocket stages, fragments from collisions. As Orion ventures beyond LEO, the density of human-made debris decreases significantly. However, the threat of natural space debris, namely micrometeoroids, persists. These are tiny particles of rock and dust, often no bigger than a grain of sand, but traveling at incredibly high velocities, tens of thousands of miles per hour.
So even something as small as a grain of sand could cause serious damage at those speeds?
Precisely. At hypervelocity speeds, even a tiny particle carries an enormous amount of kinetic energy. An impact from a micrometeoroid could damage critical external systems like solar arrays, communication antennas, or radiator panels. More dangerously, it could breach the spacecraft's hull, leading to a slow or rapid depressurization of the cabin, which would be an immediate, life-threatening emergency for the crew. Orion is designed with some shielding, often multi-layered Whipple shields, which are designed to shatter incoming particles before they reach the main pressure vessel, but no shielding is foolproof against every possible impact.
It seems like every phase, every system, and every external factor presents a unique set of challenges and potential points of failure. It really underscores the incredible complexity and inherent danger of deep space human exploration.
It really does, Alex. And while we're discussing what could go wrong, it's vital to remember that NASA and its international partners have invested decades of research, rigorous testing, and painstaking safety protocols into the Artemis program. Every single component, every procedure, every contingency plan has been scrutinized to an almost unimaginable degree. The goal isn't just to launch, but to launch safely, complete the mission, and bring the crew home safely.
That level of preparation is astounding, but even with all that, the universe is unpredictable. This mission is laying the groundwork for Artemis 3, which will land humans on the moon. So understanding these risks now is not just about the safety of Artemis 2, but also about learning how to mitigate them for future, even more ambitious missions.
Exactly. Artemis 2 is a crucial stepping stone. It's pushing the boundaries of what Orion and the Space Launch System can do, testing the life support systems for an extended deep space duration, and validating the radiation shielding and navigation techniques far from Earth. Every piece of data they collect, even from those minor anomalies like the toilet issue or the unexplained smell, is invaluable for refining the systems and procedures for future lunar landings and eventually missions to Mars.
It's a testament to human ingenuity and courage, isn't it? To willingly face these immense risks in the pursuit of knowledge and exploration.
It truly is heroic, Alex. These four astronauts are bravely venturing into the unknown, knowing full well the dangers involved. Their dedication and the dedication of the thousands of engineers and scientists on the ground is what makes these missions possible. It reminds us that while we focus on what could go wrong, the incredible triumphs of space exploration are built on meticulous planning, continuous innovation, and an unwavering commitment to overcoming challenges.
Absolutely, and as they continue their journey towards the moon, we'll all be watching, hoping for a flawless mission and a safe return. It's a powerful reminder that even in our modern age, exploring space is still very much an endeavor on the bleeding edge of human capability.
Indeed, Alex, it's a high-stakes adventure and the entire world is holding its breath with them. We're witnessing history in the making, and it's a privilege to see humanity push beyond its terrestrial boundaries once again.